Welcome to another session of Bioenergy Technologies. So, in this session, we will discuss about cook stoves, that is the biomass based. So, most of your house we are using biomass based cook stoves other than our LPG or other electric stoves, and these are normally made of metal, mud, refractories, or various uh, designs are available with and without chimney also. And normally the chimney based stoves are considered superior because due to the less indoor emissions. So in chimney based stoves the emissions will be ejected outside the house, so they are considered superior. But the problem with this no, conventional biomass based stove is that their efficiency, their utilization efficiency, which is determined by water boiling test. So normally the base efficiency of a stove, whether it is LPG or biomass based cook stove, they are determined by water boiling test. That is by boiling a particular quantity of water and measuring the temperature and the input, etc. So that is around only 10 to 8 percentage, 20 percentage only. But the conventional biomass based cook stoves, the efficiency is 10 to 20 percentage only. But if you conduct this boiler water boiling test for kerosene and LPG, etc., they are having very high, that is 65 to 70 percentage of water boiling test efficiency. And why this happens? The question is why there is this drastic reduction when you are using biomass based cook stove. We are getting only this 10 to 20 percentage, whereas the LPG and other kerosene, etc., we are getting liquid fuels, we are getting 65 to 70 percentage. So the answer is the efficiency is in biomass based stove, it is very much related to the stoichiometric air fuel ratio. That is, if our stove is working near stoichiometric conditions, there will be a very good peak combustion temperature and we will get a good efficiency. But normally our biomass based conventional cook stoves, their working will not be in stoichiometric region. They will be either rich or lean air fuel ratio is used because they are free convection based. So normally our house, etc., we have a stove, biomass based stove, which is used wood, mainly wood, coconut shell, etc., as fuel, and they are not having any forced convection. No air supply is there. There is only the air is taken by natural convection. So that quantity will not be any near to stoichiometric air fuel ratio. That is the reason, main reason why we are getting this less efficiency. And another thing is in this biomass based stove, some regions the air will be going without participating in combustion, whereas some other regions we will be very less air will be there. So that is another problem associated with these stoves. Then in addition to this, if your biomass is itself is a wet biomass, that will lead to heavy pure combustion and heavy smoking. So the quality of biomass is also important. Now we can improve these problems related to biomass based cook stoves. One is we can improve the biomass quality. So that is, if you are using a dry biomass or if you are using a pelletized or this briquette like biomass with density is high, we will get a good combustion. Then another one is to improve the compression aerodynamics. So first one is, if you improve the biomass quality, it's a moisture content. If you reduce moisture content, increase density, etc., we will get a good combustion. Another one is the design, that is the combustion aerodynamics of cook stove. So if you improve these two, its performance will also improve. So improving combustion means we have to supply air at the right airfill ratio by a fan. So this is what we can do. So instead of doing natural convection type biomass stove, we can put a fan, small capacity fan, and we can give the exact air required for stoichiometric combustion. So that we can do for improving this performance. And normally a domestic stove that is used for household purpose, its power should be approximately some 3 kilowatt heat is required. 3 kilowatt thermal heat is required. So that is around approximately some 12 gram per minute biomass consumption. So that type of stoves will consume around 12 gram of biomass per minute. And our aim will be minimizing emissions. First one aim is minimizing emissions like carbon monoxide, hydrocarbon, unburned hydrocarbons, salt particles, etc. Another one is maximizing the combustion efficiency. These are the two important objectives while designing your cook stoves. That one is minimizing CO emissions. Another one is minimizing CO emissions, hydrocarbons, particles, etc. and maximizing the combustion efficiency. Then our life of the stove must be at least 2 to 3 years, because we have to use in a continuous way, and our cost must be affordable. Then two types of cook stoves designs are available in different literature. So one is this household type, which is having around this 3 kilowatt capacity and 12 gram per minute biomass consumption. Then another one will be for a slightly large application like industrial application, that is for restaurants, community kitchens, bakery, hotels, etc. They require some larger capacity of cook stoves. Around 25 kilowatt thermal input is required. So that will be around 100 gram per minute biomass consumption. So, and another one is they should operate continuously. So not like household, where household we don't have to operate continuously, maybe maximum 1 hour only we can operate. But in industrial application, these stoves should be run continuously. So that is the basic difference compared domestic and industrial. Now in this we are discussing a new type of biomass stove, that is the pellet gasifier stove, or it is also known as the gasifier stove. So that is entirely different from our conventional stove we are using in our house, etc. So let's see the basic principle behind this gasifier stove. This is basically the major the work based on Dr. H.S. Mukunda, the former IAC scientist. So he had done he is one of the renowned combustion scientists in his period, and basically his works, he discussed this gasifier stove and created different types. So basically this gasifier stove, its design is taken from a rice hull gasification system. So this rice hull gasification system is something like this, and here we have a vertical cylinder, and the rice hull will be filled with this cylinder, and air will be drawn from the top through this packed bed, and this combustion gas will go through this grate outside. So the flame will be propagating from here to top to bottom, and the hot char will be here, and combustion gas will leave through the bottom of the grate. So this is a simple rice hull gasification system. So this was there very early, that is in China in 1967. This type of gasifier stoves, not gasifier stove, this type of rice hull gasification system was there, where air is passing from the top through a packed bed of rice hull, and it goes down through the grate. And in this one we can also use the wood chips and pellets other than this rice hull. Now if the reactor is inverted, suppose this reactor is inverted, then that will act as a reversed downdraft gasifier. So this is a downdraft gasifier. This rice hull system is a typical downdraft gasifier system because air is flowing from top to bottom. So that is an example of a downdraft gasifier. Now if you revert this particular gasification system, that will act as a pellet gasifier. So let's see how it is. So this is a reverse of that. Here you can see the air is passing through the packed bed of these pellets or wood chips. So air is going from from bottom to top, and combustion gas will be here. Combustion gas will be here after gasification, and hot char will be just below that. And the another thing is, here we have two streams of air. So first you can see a primary air. So primary air is used for gasifying these pellets or wood chips, and so that we will get some combustible gas here at the top of this bed, and we will ignite that combustible gas with the help of a secondary air. So we can see a secondary air going through this. So this is the top view and this is the front view. So this figure is very important. You have to draw this figure, and so here we can see it's using forced convection. We are using a fan here. So we have a fan which is supplying air, and two valves will be there which will control the secondary air flow rate and the primary air flow rate. So in this stove, primary air flows from bottom to the top, and the biomass is burned, and we will get a combustible gas above the top surface, and that is burned with the help of ambient air or additional secondary air. And normally the gas coming out of the bed will be at a temperature of around 800 to 1100 Kelvin. So that is the temperature range of this gas coming out, and that is mainly consists of carbon monoxide. So this is a gasification cum stove. That is why it is known as a gasifier stove. So first we are gasifying these biomass pellets with the help of sufficient primary air. Then that combustible gas, which consists of carbon monoxide, hydrogen, methane, nitrogen, etc., and some higher hydrocarbons, they are again burnt with the help of secondary air, and they are converted to carbon dioxide and water in the top region. So that is the concept of gasifier stove. So we are first gasifying biomass with the help of primary air, then that combustible gas is burnt at the top with the help of secondary air. And here another advantage is the combustible gas produced bears a fixed ratio to the amount of primary air. So if you want to increase the power of this particular stove, just we have to increase the rate of primary air, because as the primary air increases, the amount of combustible gas will also there is a relation between that. So that is how another advantage it is related, that is the primary gas amount and the amount of combustible gas produced is related, so that we can change, if you want, we can change the capacity or power of this particular gasifier stove. Then increased amount of biomass is consumed when primary air flow rate increases, hence the power of the stove is proportional to the primary air flow rate. So that is the main thing. The power of this type of stove is directly proportional to the quantity of primary air supplied. Then we will have a brief. So already we have understood what is the conventional stove, which is based on free convection. Then we have these type of gasifier stoves which works by forced convection. Now we will compare these two stoves. So we know that nearly all the domestic cook stoves in the world are mostly free convection based. So in this free convection based stove, the problem is that quantity of air or that driving potential is so small, so that the smallest ambient disturbance will affect the airflow through the stove. So that is we know that in our house, suppose we have a stove and it is igniting. Now if you want one person or another, some block is there in the path of that air, in front of the stove, that disturbance will affect this airflow through the stove and its performance will be reduced. And another thing is this randomly located and moving firewood pieces will cause a varying heat release. That is another problem. The heat release will be highly varying, because as the biomass is consumed, this wood piece will move, and then this will cause a very widely varying air fuel ratio also. And these high variations will reduce the peak flame temperature. So free convection stove, the flame temperature or the peak maximum flame temperature will be less, and it will leads to the emission of high carbon monoxide, unburned hydrocarbons, particulates, etc. So that will be very high in free convection based stoves. And another big problem is this free convection based stove, how we are going to increase the cooking speed. Suppose we have to cook faster. Normally what we will do, we will put more biomass and more wood. We will introduce more wood in it, in that small space, but without changing any air supply. That is the important thing. In free convection based stove, if you want to increase the power or high cooking speed, etc., we will give or we will put more biomass in it without changing any air supply, because we cannot change any air supply. It is only the air induced by free convection that will be no, we cannot change that, unfortunately. So even though we are putting more biomass, it will result in incomplete combustion and more emissions will be there. That is the biggest problem associated with this type of stove. So therefore these emissions and efficiency, etc., will be very badly affected in this type of stove, this natural convection based stove. But only advantage is the free convection stove, we can use any non-processed biomass, like any wood, with any biomass type we can use. That is only advantage in free convection based stoves. Now coming to forced convection stoves, the only problem or disadvantage is we require some electricity, because we are using a fan for supplying air, whether it is primary air or secondary air, etc. We are using a fan, so we require some electricity for running that fan, and that will be difficult in some rural areas where electrical supply is very difficult. This is a problem faced by this forced convection stove. But we have in recently, or we have the availability of mass production of computer fans. We have available computer fans are largely available with small power range, and their electricity, they can even storage batteries, because their power is very small. We can run that type of fan with the help of a storage battery. So that is a development in recent times, so that we can use forced convection based stove even in rural areas with the help of a battery. And these fans are available in 1 to 2 watt, very small range with very low cost. And gasifier stove, already we have discussed what is gasifier stove. So gasifier stove loaded with this fuel is an alternative to free convection stoves. So this is a very good alternative to free convection stoves. And at any fixed power level, the gas composition and temperature of this type of gasifier stove will be constant. With the appropriate secondary airflow, we can maintain a constant peak temperature for this type of gasifier stoves. And if you want to increase the power, we will increase the primary airflow rate, and it will take a transition time to reach a new steady state, a few minutes it will have some unsteady behavior. After that it will reach a steady state. So that is the advantage of this. Another advantage of this forced convection gasifier stove, we can very easily increase the power because we are also increasing the air without any problem. But in natural convection stove we are not able to increase any airflow rate, we can only increase the biomass feed rate only. So in that case we will have some problems. And so gasifier stove provide a good flame control to the user and make it less user dependent for achieving the desired efficiency and emissions. So our natural convection stove depend mainly on persons, how they are using that, like that. But this gasifier stove, it is independent of these other persons. Now finally we have to discuss what is the efficiency. There's a range of efficiency and emission in this type of free and forced convection stove. This is a typical example. So first this is first free convection based stove based on mud, ceramic, metal, etc. Their water boiling efficiency, so WB is water boiling efficiency, they are very less. They will be only 15. In some stove they are 15. They are highly varying also. Some stove they will be 15, some around maximum is 35. But mostly this stove will be around 15 to 20% only efficiency, water boiling efficiency. But here you can see the fan based stove, that is a forced convection stove, it is 35 to 45. As increase, our efficiency is increased. And again for an optimized gasifier fan stove we have discussed, it is again increased to maximum of 40 to 50%. So this is the efficiency comparison. And if you consider the carbon monoxide emission per gram per megajoule of heat used, here it is 1.5 to 15. That is a high quantity of carbon monoxide emission is there in natural convection stoves. But in this forced convection it is only 0.8 to 1.2. And our gasifier stove it is again 0.8 to 1 only. So they have a drastic reduction in carbon monoxide emission. And particulate matter also, particulate matter in milligram per megajoule, this is very high. You can see the particulate emission of natural convection stove is 30, to some case it is 1000, very high particulate emission. But fan based stove it is only 2 to 20, and gasifier stove it is only 2 to 9 only. So we have in gasifier stove is very good in performance when you are comparing emissions as well as efficiency, comparing to our conventional natural convection stoves. And this is a typical plot of carbon monoxide efficiency and carbon monoxide emission y-axis and efficiency in x-axis for different. This is from different literature. So this is the old and free convection stove. They lie in this circle. That is, their emission is very high. You can see, and their efficiency also very low. But these forced convection stoves and gasifier stoves, they are lying in this circle, that is their emission is less and efficiency is very high. So this is a comparison from literature by Dr. H.S. Mukunda. So you can see quickly, you can identify the free convection based stoves, what are their performance and emission, carbon monoxide emission, and what is the performance and emission of forced convection stoves. So wide range of efficiency and emission in free convection based stove is there because there is no possibility of controlling the emission. So it is a random event. So in free convection stove we are not able to control any airflow rate. So it will depend on different experiments. So that is why we have a wide range of efficiency and emission is here. So from all these it is very much clear that a fan based stove which operates near stoichiometric condition is far superior than free convection stove. That is the conclusion we are obtained from this comparison. So we have to switch to fan based stoves. We are all the households we are using free convection based stove. which having less efficiency and very high carbon monoxide and particulate matters emissions. So if you are switching that to a forced convection stove properly designed with good stoichiometric air supply, it will be better. And if you are using gasifier stove, it will be very good applicable. So HS Mugunda has done to develop many models on that gasifier stove, and he has developed some Urja and some Swasti. These are the names of stoves developed. If interested people, you can watch the study the literature. So he has done different designs, household design separately and for industrial applications separately, and that is available commercially with they are producing as a company. So we have to switch to that type of towers, then only we can improve the efficiency and reduce the emissions. So with this we are stopping this. Thank you.